Okay, thank you very much for the opportunity to give a talk here about the virtual laboratory for distributed systems research. In general, the idea of this tool is to support not only computer scientists, but also many other scientific efforts for other research directions, like biology, chemistry, or economics, for example. Every researcher dealing with distributed systems can use this tool in a certain way. One point is what I want to talk about here, some examples in research, and especially about MARCHI. And MARCHI is a new joint research effort funded by the German Research Foundation at the University of Darmstadt. It's a large project running maybe for 12 years. There will be 2 re-evaluation phases, but when everything went well, this project can run for 12 years, and this is a great opportunity. Okay, what I want to talk about, a little bit for introduction about GLab and the lab itself. Then I talk about this tool for distributed systems research, which is called Topology Management Tool. I will give an outlook a little bit about the footprint, what it is right now, discuss some use cases, and last but not least, what I want to discuss is about the testbed on demand. Okay, this is the outline of the talk, and well, this is the beginning, and as we just mentioned before, GLab was a project which runs more or less in the same time frame as the GENIE project in the US. And it was that some guys from the GENIE project were in Germany, and they talked to the Minister of Research and said, well, the National Science Foundation is going in a big project about future internet. And then the German Research Foundation said, oh, they are going in the direction of future internet research. This must be a big thing, so we have to do the same. And this was the generation of the GLab, the German lab project in Germany. But nevertheless, from the early beginning of the project, it was a close collaboration between the GENIE guys and the GLab guys in Germany. The main idea here, which separates the GLab project from other future internet projects in, for example, in the European context, is that we have on the one hand the basic research project in itself, yes, dealing with some new algorithms for the internet and so on. And on the other side, we have an experimental facility where these algorithms can be implemented and tried out whether the algorithm works or not. Right? And when one finds that the algorithm had some obstacles, the can go back to the research projects, and the research project can fit the parameters, bring it back to the experimental facility, and so in a spiral process we will come into the end based on the future internet. So the future internet is not, from my point of view, is not a replacement for the current internet, but it's more an outline of a research area or a research idea in itself. This was the GLab project, and the GLab project in its first phase deals mainly with the basic internet architecture. The idea was in GLab here to depart from the layered architecture of the internet to a more, well, flexible way of architecture based on so-called building blocks, where the building blocks can be combined into so-called protocol graphs, where these protocol graphs can dynamically support certain demands of the applications or capabilities of the underlying networks. So in general, there was a huge research effort in the architectural area. We had some work packages about routing and addressing. Wireless networking and mobility were the big issue in the project. Then monitoring and management concepts, quality of service, security, and architecture and composition of services. These were the overall structure of the GLab project. And beside this, to try all these algorithms which are developed in these work packages, to try them out, there was an experimental facility which was owned by the same institutions where the different work packages was spread out. Yeah, so that each university was responsible for the research project itself as well as for the experimental facility. And when you look to other projects like PenLab in Europe, it was only an effort in setting up an experimental facilities without any users. And this was so that these projects are going to find out some guys using their platforms. Okay, the lab itself, it was distributed across 6 sites. These are the main or the starting sites which we had in Germany. It was Berlin, Darmstadt, Kaiserslautern, Munich, Karlsruhe, and Würzburg. These are the basic the starting point of the GLab project. The central administration of the lab itself was in Kaiserslautern. There was the largest site for GLab in Germany, and the connectivity of the different sites were realized by the National Research Network, by the DFN-Verein in Germany. Another point was that each institution, each site here, had its own control over the whole over their own infrastructure. So when the site at TU Darmstadt said, "Oh, we have a project and we need our resources completely by our own researchers," one should able to bring them out of the complete infrastructure and they can use them by themselves. Yeah, so decentralized resources can be independently used. And one point, and this was not really realized, we want to have tests on lower layers, especially layer 1 topologies based on optical networking, lambdas and other things. But unfortunately, due to the pricing of the German research network, it was unable to realize, so that we had to find out other ways to test and to operate with lower layers. Another point, how can we set up the control frameworks? And because we want to have a head start of the project, we decided first to go with PlanetLab. And PlanetLab, as a distributed operating or control framework, is well known. And then we had a good cooperation with University of Princeton, where it comes from. And we set up a private PlanetLab at Kaiserslautern and organized the different sites here to run the PlanetLab nodes. But over time, we have seen the 7 different work packages. Some researchers came out and said, well, the infrastructure of PlanetLab does not offer the right infrastructure and the right functionality which we want to have to run our projects, to run our algorithms, to run our problems. And then it was a decision that said, well, let us have another abstraction. For example, the abstraction for PlanetLab was a slice-based abstraction, and we want to have a so-called topology-based abstraction. And that was the starting point of the development of the topology management tool. Further on, we had some interfaces, so we said, well, it is important that GLab does not stand for itself, but GLab has also some interfaces, some federation with other testbeds. And other testbeds here, for example, it is Genie, it is PlanetLab Japan, WinLab, and WinLab is a wireless or wireless testbed at Rutgers University, and it's also important to have some cooperation with these networks and to have some access to the resources there. Another point, and which we want to have, namely an open flow setup from the early beginning of the project. And so during the solicitation of the hardware platform, we asked the vendors, are you able to support open flow? And we said, well, yes, we are. Especially Cisco said, yes, we can support open flow, and but not yet. But be quiet and half a year, and so then we can equip all these servers and all these systems and sites with open flow capable switches. Unfortunately, Cisco does not, and so it was a big problem that we couldn't start with the with OpenFlow capabilities from the early beginning, but what we did, namely that we, during the development of Tomato, we decided to implement the Open vSwitch and other software-defined control frameworks so that we can do OpenFlow experiments also in the testbed itself. Right now, we are able to have also hardware-based OpenFlow switches, and these switches were from NEC, and most of, or some of the sites, for example, Darmstadt, Munich, and Kaiserslautern are equipped right now with the OpenFlow switches from NEC. Okay, Tomato, the testbed itself, part of the German lab research project in the work package 7. From its early beginning, it was clear that we want to develop a tool which is open source. And so we decided very early, and this is at version 2.0, that it is open sourced and it is hosted at GitHub. Therefore, we hope that we can get some collaboration institutes which are able or willing or want to have support us a little bit in the further development of Tomato. Another point, Tomato can be used completely independent of GLab. So GLab, all the resources which we have, is not mandatory for running GLab. When you have your own hardware sites where you can run it, you can do it. Currently, we have 12 partners, partner institutions worldwide, especially some in the US. More than 122 nodes, up to 256 gigabyte memories, and the most advanced systems had up to 24 cores. The main abstraction of Tomato is the so-called topology-centric development based on virtualization. So each experiment which can run on Tomato has its own virtual network topology, virtual host, and each topology is self-contained. So that when you set up a topology, this topology is completely independent of the internet. There is no open access to the internet. And the one topology is completely independent from another one. To deal with it, we have developed a so-called web user interface, where the web user interface allows you to define or to design your topology on an easy drag and drop way. Yes, and it's clear, easy drag and drop. You can do it when your infrastructure or your topology is a very small one, up to 10 or 20 hosts. You can do it by drag and drop. But when you have hundreds, it's a little bit complicated or not so easy to do and not so convenient for designing these topologies. When you are finished with designing the topologies, you have the end hosts, the virtual machines, and you can have direct access to these virtual machines based on VNC console technology. Advanced features, so when you want to create a larger topology, hundreds or more than 100 nodes, then you can do it on some scripting interfaces, and the scripting interfaces is a JSON-based description language for import and export of such topologies. And there is a Python XML RPC API, which also can be used for controlling and to manage the whole infrastructure. So what I said before, Tomato is topology oriented, and topology orientation means the basic abstraction is a topology and hosts provide virtual components. These virtual components or the topologies can be structured completely based on these virtual components. Tunneling, or when you have the different components of a topology, you can combine these topologies by tunneling and stitching, and all these technologies are introduced or inserted automatically. Yes, it's not up to you to create all these sophisticated links and the endpoints and so on. This can be done automatically. And the topology itself, the tomato topology itself, is not restricted to the underlying physical topology of the network. Yeah, so you can have arbitrary topologies. For example, here when you want to create an experiment with multi-homing, you can do this. Also, the underlying network topology does not allow or does have not multi-homing environments. On the other hand, when you have Planet Lab and Genie facilities, these are slice-based. Yes, and a slice is a subset of the existing topology. Yes, you cannot change the existing topology there. And networks are isolated by VLANs. And topology is, as I said, restricted by the physical topology itself. The practical differences here is that the topology of Tomato is completely virtual, and so you have routers, hubs, switches, OpenFlow, and so on. All these endpoints or all these components are virtual components in the technology. And as I also said before, it was that we want to have a layer 2 technology to combine or to have an interaction between different sites in Germany. But because it was too expensive, now we had a technology implemented that allows layer 2 tunneling over physical layer 2, so there is no need for physical layer 2 connections. Yeah, so that we can have layer 2 tunneling over UDP and can make experiments based on the on layer 2 tunneling. Another point was the ability to multi-homing, also when no site is multi-homed itself. Framework comparison, when we have a look at different testbeds or testbeds and technologies. So on the one hand, we have the so-called Emulab. Emulab is running at Utah, University of Utah, and when you want to run an experiment there, you can do it, but real hardware, close to the hardware running experiments. And then it makes sense to use kind of Emulab, which means you have realistic experiments based on direct hardware access, but the number of experiments, the parallel number of experiments are very limited. On the other hand, there is another project which comes from the Genie project, which is called Seattle. And Seattle is a wonderful Python-based infrastructure from University of Washington, coming from Justin Kapos. And this was an idea, in the end, the so-called 1 million nodes Genie. Yeah, and it's an easy tool, easy to learn, based on the Python language, and it can be used, for example, in classroom teaching. And in the middle of this line, we have Planet Lab with a little bit parallelism and realism. To overcome these, two edges, Tomato tries to create a virtual topology based right now on KVM, where KVM is a very heavy-weighted, or yes, KVM is a full virtualization technology, and therefore, more or less heavy-weighted, so that not too much of these virtual machines can run on a real machine. OpenVZ is much lighter, and therefore we can run a lot of such virtual machines on a certain server, and we can also use from the CL project the so-called restricted Python dialect, and based on the restricted Python dialect we are able to run a lot of parallel experiments in this line. What does it mean? When you compare Planet Lab, Emulab, Seattle and the Tomato framework, you can see that it depends on the demand of your experiment. It makes sense to use one or the other control framework. Yes, for example, when you have or when you need real hardware access, the Emulab environment is really the best thing to do or to try it out. On the other hand, when you see Tomato more or less can support most of these attributes here, beside the physical hardware access. physical hardware access is not possible right now. And when you have very high traffic and you want to test very high traffic systems, then it's also a problem to deal with Tomato. The architecture of Tomato itself, well, it contains first on the user. The user has the ability to deal with its front end. It's a web-based front end, and based on the classical web browser, the user can create the topology. On the other hand, as I mentioned before, we have also the possibility to create the topologies based on command line interfaces, the API, or by certain scripting. Yeah, so that you can create huge topologies not only by drag and drop. On the other hand, there is a backend. The backend is a central system, but not necessarily a central. We can have multiple of them. But here, all the topologies were controlled. It distributes the topology over the hosts, applies these stitching when you stitch the different systems together. It does some monitoring, user management, and it provides a so-called XML RPC interface to create the access to the facility hosts. And the facility host consists of a certain host manager, and the host manager is based right now on Proxmox, which is a certain implementation of in addition to the Linux environment. This host manager controls one host, offers virtualization, network capabilities, and controls the local topology elements. So right now, the current status of Tomato and in the context of GLab is that we have one backend in Kaiserslautern and, as I said, 12 worldwide distributed institutions running some facility hosts for dealing with the Tomato. The topology itself contains so-called devices and so-called connectors. And here, right now, we have three kinds of devices. It's a KVM device, which is here signed to be green. OpenVZ devices are blue. And programmable devices not appear in this small topology. And programmable devices are colored in orange. The graphical representation of this topology is that the icon shows the element type. The colored icons show the virtualization technology, as I said before. Link colors show network segments. So you have here blue lines, which means that this is one network element. Here you have red lines. The red lines is a second network topology. It's a second network topology, and black lines a third network topology, or a third network where this topology is connected to the internet itself. The dashed lines means that you have changed the parameters of the line. Yeah, so you can have access to the line the delay, the bandwidth, and other parameters, and you can change the parameters when you want to test or when you want to manage or test some, have some experiments based for wireless systems, for example. Per topology, you have accounting and permissions, which you can set, and you have the VPN connectors. VPN connectors are based on TINC and the external networks itself. Again, the virtual elements for the virtual machines. You have the KVM. It's more a heavy-weighted system, so it is a roughly number here. You can run, depending on the how powerful the machine is, the physical machine is, you can have up to 20 or around 20 machines. OpenVZ, you can run 100 parallel virtual machines, or with the RipI scripts, you can run more than thousands of them. Yes, and here especially important is for the KVM that nearly any x86 operating system can be deployed to these virtual machines, which means, and this depends a little bit on the licenses you have, you are able to deploy Windows to KVM systems and to try out some experiments when you need some Windows-based operating systems. But this depends whether you have the right or the license to run this operating system itself. Yeah, scripts. We have some programming language virtualization installed as software. These are the RIPI scripts, which come from the Seattle project as a restricted Python sandbox system from the Seattle project. This is modified. The restricted Python was modified for Tomato and functioned for receiving and sending raw Ethernet packages. Yeah, while in Python it was not possible to do so. Additional elements. So when you have a new idea for some of these elements, for a new element, then you can create it, and it can be easily installed into the complete architecture. Right now we are planning to develop some VirtualBox and LXC as operating systems, so that also these templates can be loaded to the virtual elements. So how to control all these things? In the beginning, when you have set up such a small topology, here we have one system which is connected to the internet. You can control these systems by right-click, and you will find these attributes which can be set. First of all, you can change the name of this special element of the architecture. Then you can create the site where this element should be deployed. Yeah, so in general, you can say when you leave this open, then there is a certain technology, load balancing technology, which deploy this special element to a server with a small load or with which is most appropriate to run. Otherwise, you can say, okay, I want to run this element especially at the site in Kaiserslautern, or the site in Vancouver, or the site in Kansas, or the site I don't know where. Another point which is important is you can change the templates. And when you choose the templates, you have different choices. For example, normally you can run the Debian Linux system. Ubuntu is available, but you can also deploy or change the template of a system to some open flow controller, as the RYU open flow controller or the Floodlight open flow controller. Yes, it's also possible so that you can have some systems which can deal as open flow controllers in your architecture. So on the other hand here, when you look to the performance profile, you can define some or how many resources your system should be used. For example, how many CPUs, how many RAM, how many disk space, and so on can be defined by the performance profile. Yes, you have a normal, you have a low, and you have a high performance profile. The network connectors and the network elements, when you want to stitch these systems together, it's based on a full meshed VPN technology, which is called TINC. And this is the full mesh TINC description of the GLab environment, not of all the hosts of Tomato, but only for the GLab hosts. It is fully contained virtual network, so that all these systems running in GLab or in this environment is completely contained and not connected to the internet. Yes, it is part of the internet, but not connected. You can not have direct access to these systems. Tunneling is based on vTun, and this is what I said before. We can do layer 2 tunneling over UDP. Open endpoints allows federation, and this I think is important, that we can have some open interfaces so that we can cooperate or federate with other technologies. External networks, bridge into local network segments or internet or local research networks. Yeah, so external network means that when you connect an external network to your topology, and the external network is the internet, then you are able to access systems from your topology outside the topology and vice versa. Yes, and SDN OpenFlow. Right now we have implemented the Open vSwitch, and for hardware switching we are using the NEC systems. I think it's OpenFlow 1.3. It's I think the current OpenFlow implementation. And for the OpenFlow controlling software, we have Floodlight and the LYU OpenFlow controller. These can be used as templates in the system. So when you have a look at the Tomato to the user interface, it is a web-based user interface here, and you can create a topology by drag and drop these elements, and you can control these elements here in a certain way. So intelligent load balancing, it depends whether you say where your system should be deployed or not. Then there is an OpenXML RPC interface. When the topology becomes too large, then or too many hosts, then it is not easy to handle it by drag and drop. Yeah, so the user features here, automatic network interface configuration. So the network interfaces here, the gray circles defines the network interface, and you can control these network interface. You can do some changes to running topologies. While the topology is running, you can change something. You have console access. You can image up and download. Yeah, so when you have a certain image which you want to, where you have designed your experiment in, you can upload this complete experiment to a certain host, and you can do some packet capturing to control the different links here. The graphical editor, yes, it's for our point of view easy to use. It's fully controlled over the topology elements, and you can show the resource usage. So for every element, you can show a certain graphs here where you have some memory usage, disk space usage, traffic usage, or CPU time usage. So for every topology or for every element, you can define these parameters. Link emulation is important. So when you have such a nice topology or small topology, these blue squares in the middle of a link, you can also have a right click. And on the right click, you get this drop-down menu, and you can control the properties like bandwidth, latency, jitter, packet loss, corruption, and duplication rates. Especially the distribution of the jitter can be chosen between different parameters here. And important is you can choose the bandwidth so that it is also possible to emulate wireless links. Yeah, so when you have an experiment dealing with some wireless technology, you can set your bandwidth to certain values, small values, and so the emulation of a wireless link can be done. You can see when you have any change in these parameters for the links will be dashed. Yeah, so you can see, okay, these links are changed, while this link is not dashed because 10 megabits per second is the basic value which is created for such links. Yes, as default. Because when an experiment runs out of order or runs out of control, the maximum speed you have, or in general, is 10 megabit. But when you said, okay, I need higher speeds at these links, you can upgrade these parameters also to higher speed. That's not a problem. But in general, it's restricted to 10 megabit. Packet capturing. So when you are interested what kinds of packet and what the content of the packets are in these links, you can enable packet capturing. And packet capturing then can be based for download, for example, and you can do some direct filtering. Format is PCAP, which is compatible to Wireshark, and all the systems then are combined to Wireshark, and you can control all the elements and all the packets and the content of the packets here, which is going over a certain link. Executable archives, also an important thing. So when you have a running topology and you have created a topology on a certain file, you can upload this file. Also right-clicking on this element, you get the drop-down menu, you get this element Executable Archive, and you can upload and download these files. Yes, and this is important so that you can do or can organize and manage huge topologies and without doing too much effort in the graphical user interface. The use cases, yes, install software packages, run complete experiments, and up and download data. Experiment lifecycle, create executable archive, upload the archive, run the experiment via a start script. So every uploaded file you have is created with a so-called start script. So when the file is uploaded, the uploaded file will start automatically and run out the experiment. After the experiment is finished, you can collect all the different results and you can download the archive. Console access, also when the topology is up and running, right-click to the element here, you can have a console access, and here first of all you have an HTML5 interface, you can have a Java applet or a VNC direct link. Yes, important here, then you have direct access, direct console access to the virtual machines based on, for example, here it's the Linux operating system, or it's also possible if you have the license to deal with Windows operating systems. So application areas. So access layer experiments, as I said before, are not possible because it is a virtualization technology, and so we cannot go down to the physical layer. So physical layers, test beds are completely different and is not supported by Tomato, but nevertheless you can do some network layer experiments. So for example, focus on TCP/IP, on version 6, for example, or TCP substitutes. This was in the GLab projects running certain routing functionalities also. So the requirements here, you must have deep operating system access, modified kernels and so on, small but complex topologies, and link emulation can be used here, and all this is offered by Tomato. On the other hand, you can have some algorithm and protocol experiments work on top of the network layer. Example, you can have experiments based on peer-to-peer or publish-subscribe and all these technology. Here you have to have the huge but simple topologies, link emulation, but no hardware or operating system access. And this is operated or organized and offered by the OpenVZ technology. Virtualization technology. Legacy software experiments, you can have, or you can use legacy software, deploy these software to the Tomato hosts, and can run this topology or this special legacy software and try out how does the software behaves and what is the network behavior of the software. So you can test here, for example, Skype or Windows. This is what we have done in the system itself. Okay, the footprint of tomato right now, we have some sites, namely in Germany, the more or less 6 sites which the German lab project start with are a partner of the the tomato environment. We have some hosts in Nordunet in Norway. We have just starting some nodes in Madrid in Spain. Then we have some hosts here, for example, is Victoria in Canada. It is Northwestern University, Chicago, Kansas. It is Clemson and is Rutgers University. And I hope that the next time we will see some nodes here at ICSI in Berkeley. Scaling up. So right now, it is possible to have a single host deployment, or the backend as well as the tomato hosts can be implemented on one single system. Yeah, so you can do it in your lab. You must have a certain system for running the tomato hosts, because the tomato hosts need the Proxmox extension of the operating system. And this is more or less easy for local tests. Then you can have isolated multi-host setups. This is how does tomato running today. In Kaiserslautern, we have one backend, and all these different sites, which I have shown before, are related to this backend. This can be done. It's a single backend and web front end. On the other hand, you can have so-called federated setups, so that the tomato host can be used by multiple backends, so that the backend will not become a single point of failure. It's easy to set up, and it can be controlled by different backends. Right now, the tomato community consists of over 122 hosts at several sites. Currently, the question is, when we're setting up the environment, so we have to deal with physical machines. So we have to buy physical machines, we have to maintain physical machines, and we have to, every few years, we have to replace the physical machines. And this was the idea coming up and said, well, would it be possible to deploy these hosts on demand to a cloud provider? But the question was, normally a cloud provider is offering virtual machines, but we cannot use virtual machines for our host services. Yes, so it is important to use cloud services or cloud providers offering bare metal machines. And this is done, for example, here in GLab. And GLab is one new project beside the, what was the other? GLab and Chameleon, yes, 2 new NSF projects in the cloud arena. And these 2 projects are offering bare metal machines, so that we can use these cloud infrastructure to deploy the tomato hosts on demand to these hosts when an experiment is running. And when you are finishing with the experiment, you can destroy all the topology and give the resources free. This is running a master thesis in Kaiserslautern, and another thing is a bachelor thesis which deals with dynamic allocation of resources, which means more or less the same, that you can have some resources which you can include into Tomato and destroy and give them free after using it. So that it is more economically than to buy and to maintain the physical systems. Use case 1, we had a simple topology, and this was a project in the area of agriculture. It was called iGreen, and iGreen means that, well, fertilizing and harvesting big farms, it is a problem of the machines and so. And the idea was to have a satellite communication to a central server, and the harvesting machines are equipped with such nice devices here. And the question was, how does latency affect quality of service and accuracy of harvesting, for example, so that a harvesting machine does not harvest the field of your neighbor. Yes, but that was a question: how can is quality of service and accuracy affected here? And here we have used the attribute changing of the link emulation, and we said here that the link should have 2 megabits on up and download, and you can change it and you can simulate in this sense how does a difference in access speed can influence the accuracy of these harvesting or virtualizing of fields. Another use case was a malware analysis, and this was another idea. It was a former worm of the Windows operating system, and therefore it was necessary to run the victim on KVM, on the Windows system. And first of all, we set up this topology, and first we connected the topology to the internet so that we could download the virus to the victim, to the KVM machine. Then we killed this connection to the open internet, and because the topology itself is completely self-contained, we could start the virus at the system based on the VNC front end, and we could start it, and then we can monitor the different links. What is the virus asked for? Yeah, where are the hosts of the viruses? What does the virus want to do? And to whom the virus want to connect to? And all this stuff. And this could be done based on the packet capturing and the monitoring of the links. Just running project, and this is within the new Maki project and the collaborative research project of the University of Darmstadt. It is based on transitions in overlay-based streaming systems, and here the scenario was they needed more than 100 machines, different machines across different sites, real and emulated network parameters, and then they could set up such an much larger topology than we had seen it before. And what they did right now, they planned the usage of open flow control software based on the Open vSwitch and on the hardware switches, but this will be the next steps. Steps taken here right now: study of available features, first proof of concepts, so what can be done on the Tomato front end. But to create this topology, it was done by scripting and based on the Tomato Python API. The idea here, or the Tomato API, is a quite simple programming language. You can create the whole topology by create the hosts, the nodes, the different nodes. You can say which site, University Kaiserslautern, the position where the system or the host should be positioned on the graphical front end, and so on. You can create the switches, and you can create some actions which should running on the hosts. Yes, lesson learned here: runtime consuming actions in parallel. Yes, use Linux, Windows works, but it tested well and requires changes to the framework. So right now the project is just running for 2 years, and the first experiments are just started now. Testbed on demand. Testbed on demand, this was a point I also mentioned before, the current developments, extending and improving the Tomato testbed, early work on scalable federated clouds, and Kaiserslautern has become a so-called associated partner of the GLab project. Yeah, so that we can use it. All the infrastructure and the GLab project right now is implemented based on Utah, on the Salt Lake City. It is Clemson, South Carolina, and it is Wisconsin, Madison. These are the main sites, the 3 starting sites of the GLab project. GLab is NSF funded. Kaiserslautern has become the partner, and GLab offers here the bare metal machines, which we can use to deploy these hosts. This is the idea, and to control these hosts by the backend and the XML RPC mechanisms. And when an experiment is over, we can destroy the topologies and give the resources free. Yeah, this is the current network connectivity which we have from Kaiserslautern site. We are going from Kaiserslautern through the German National Research Network, Géant 2, this is a European network, Netherlights, then Starlight is in Chicago, Internet 2, and then going to Clemson. Right now we are operating in stitching all the different network topologies together, and I don't know what is the current status of it. It's still not working because stitching, well, should be an easy thing, but in general it takes some time. But we are hopeful that we can have success in the next few weeks. Okay, let us summarize here. Tomato is a network experimentation tool. And from my point of view, it is not only useful for computer scientists, but it can be useful for every research dealing with distributed systems, whatever that means. It is based on virtualization. Right now, KVM and OpenVZ are the basic elements which we have created, but we are still working on it based on bachelor thesis, master thesis, and we have some advanced capabilities which can be done with PhD theses. And so we hope that maybe some of you guys might have some interest in working in this context, and we are open and very glad if you ask us to become partner of the project. It's an easy-to-use graphical front-end, open source since 2.0, and it is ready to use. Here, the link tomatolab.org. You can find out some screencasts, some more information about it, and you can join the Tomato community first, maybe as a user. Then you must ask for access to the network, and from Kaiserslautern side we will grant an access for using it. Or you can use Tomato as an institution, and then the idea is to offer some machines so that we can run the Tomato host on these machines, and you are able you can use the complete infrastructure which we offer from Tomato. Yeah, feature-rich environment for research and teaching, and we see that some universities in Germany using Tomato for teaching, for simple network technology teaching, like dealing with delay, dealing with jitter, and so on. This can be easily done in classrooms. Sustainability, so the project itself started in the ICSI, in my Integrated Communication Systems working group at Kaiserslautern, and right now we have handed over to the data center in Kaiserslautern to have some sustainability, to have some personal support, to run the system, to monitor the systems, and so on. But nevertheless, also we are looking for new partners, as I said before. So part of the new research projects like Maki offer us some new machines. Yeah, so that the German Research Foundation is funding the replacement of the machines. And when a new project is coming up in this arena, then they can apply for some money to support the framework itself. The worldwide footprint, this was the slide I showed before, and hopefully we can convince you to set up 1 or 2 hosts here at Berkeley so that we can deploy the Tomato host also to here. Testbed on demand, this is a point which is very important for future, because it is very expensive to run hardware and to run all these infrastructures, so it would be easy to do it on demand. We will have some discussions with bare metal providers. Right now, the GLab project and Chameleon, but I think there are some other commercial providers for such machines. But unfortunately, right now, it is not Google and it's not Amazon. But I think it's a question to the contacts of Google and Apple who can offering these systems, but they have the systems. Right now we have no contact persons, so that we first concentrate on GLab and Chameleon. Okay, some questions. And okay, this is my business card, and I will, or I have the PDF of the presentation, and I think I will send you the presentation, and you can distribute it to whom are interested. Here are some literature dealing with tomato and the GLab approach, and thank you very much. Okay. Yeah.
I'm curious how you handle research between multiple virtual networks. So a bunch of people say they want, 10 gigabits across the globe, and they try and actually push that. Are you just, is it an on-demand thing, or do you provide guarantees? Or not that it matters too much for researchers, but I'm just curious. There's an interesting allocation problem.
Yes, I think there is an interesting problem, and right now, especially the link which I showed between Kaiserslautern and Clemson, it's a 1 gig link, and we want to upgrade it to 10 gig. And this is a question. The demand is there, but it is too expensive for us. Currently, we have the link from Frankfurt to Clemson. It is supported by the GLab 2, the network in Europe, and from Starlight. And the link from Frankfurt to Clemson is completely free of charge. We have to be charged from Frankfurt to Kaiserslautern, the last mile, and this is for a 1 gig link about 3,000 euros, and for a 10 gig link it will be up to 10,000 euros. And so when there is some demand or some research projects where the research projects can apply for such money, then we are able to do it. Yes?
I mean, right now, if there's oversubscription, do you just allow it to be oversubscribed, or do you?
We allow it, yeah.
Is it the same for the machines? Do you also allow oversubscription there? Because I used GLab in the past, and that was a big problem that these machines were not responsive enough for certain applications. So, do you include it currently? Or?
The load balancing will not allow more machines than the host can handle.
Okay.
But up to that limit, it will just do it.
And you can also have a physical core if you need it, or
no, there's no resource reservation in any kind.
Okay.
What is the primary driver for getting more sites to participate? Is it to get access to more machines, or is it to also exploit the specifics of the link?
I think it is the idea to have more sites and to bring the Tomato tool itself into the discussion. Yeah, so that though Planet Lab around the world is well known, Tomato is not. Yes, and therefore, as more sites we have and as more researchers are dealing with the tool, the more the tool will be known, and then in the end, we will get some funding or some financing of maintain and so we have to have some developers like Dennis Schwerdel, and we have 2 other students in Kaiserslautern and some guys in Darmstadt, but that's not enough, and that is a question: how does the development can be sustainable over the next years, and therefore that. As more as resources we have, as more people we have dealing with this tool, the better it is to go into the future of the tool. Right.
So, but that means from the perspective of an experiment, it doesn't really matter where the machines are.
Right. Yeah, sometimes, especially the guys from Markey, when they do some video streaming, they want to have some machines abroad, namely in the US. Yes, to have.
Sure, but in principle, I guess you could simulate the same link properties with your
That's yeah.
Well, in general, the internet should be the same everywhere. But we all know it is not. So basically, from some IPs, you have access to some sites which you cannot access from different IPs. So you can do some interesting things using all these IP addresses that you can get from all around the world.
Except that I think you guys said you don't have external connectivity.
Oh, you can pull on the internet from any site you want and connect your host to it.
Yeah, then I see.
Yeah, these are the external networks, and when you have the host, you can connect an external network to the host, and then you have and you can have these access not only from side of Kaiserslautern, but you can have also access from University of Vancouver, for example.
One question I was wondering about the bare metal restrictions. So why can't you integrate EC2 machines into the setup? I mean, you guys already have like different types of nodes. I mean, there are certain restrictions coming in there, but
yes. So basically, if you know how DINI facilities work, they basically provide virtual machines, and everything you want to do with them is on top. So if you want to have virtual networks, it's on top, and everything. And we have different idea by having this all transparently beneath the virtual machine. And if Amazon only gives you a virtual machine, you cannot get beneath it. You cannot add a tunnel beneath virtual internet.
could you build your stuff inside that virtual machine essentially on top? You build another tunnel.
Yes, but there's a real problem of stacking virtualization technologies inside each other. That is currently limiting us.
Okay.
Yeah, and sometimes we are using directly some features of the processor. And when these features are not available to the tomato hosts.
I understand that, though. I was thinking, I mean, you already have different types of nodes anyways. Like the Python version can do less. I assume it's, of course, less than the
Templates, different templates, you mean?
Yeah, different features. I mean, you can't...
Yeah, clear. Yeah.
Yes, but that's not different types of hosts. Different types of virtual machines that you can get. So if you want to use Amazon as a host, then we could not provide KVM because KVM does not stack inside Amazon. So in principle, we are prepared to actually use Amazon, but then we could not provide KVM machines on those hosts. That's not the primary direction we're going.
Yeah. So the question is, what about these hosts? And inside the host, when we create the virtual machines, then we can use different templates. But the host has some restrictions.
Yeah, thanks again.
Okay, thank you.
There should be Tuesday, right? So there should be cookies outside.
Okay, fine.
So Tuesday is cookie day or?
Tuesdays and Thursdays.
Tuesday and Thursday.
Okay, we do it twice a day. Welcome to X.